Yeah, hi, thank you. That was a great introduction because so many people, they don't know NVIDIA has an office here in Zurich as well. We do a lot of software, we don't just do GPUs. But yeah, as you said, we're going to talk about applications and recent advances of deep learning for robot navigation. So yeah, moving robots. So we're back to all in silico, basically. Coming back to what other speakers also have said, if you move a robot, there's different levels to it, and you need to solve one before moving on to the other. And as Andrew Davison put, who is a famous researcher and also still a very recent and current researcher in this field, he said that the basic level is the robust localization. So Margarita talked about this, Alexander talked about this, very important. And the next step is the dense mapping. So the robot needs to map the environment, to build a map. And what my project was about the semantic understanding. So once you have that, you try to build on top of that, something that makes the robot smarter. And in my example, I was working also with these hyped deep learning technologies. So what you can see on the left is a more classical example of robotics. So you have this drone, it's flying around, it's localizing itself using these very sparse points, but they don't mean anything, they're just points in space. And what you often see, or in the recent years with this hype of deep learning, it always lives in the image. And what I try to do is I try to move it towards the 3D space, same as the other application you see on the left. So on the right you see one example, you have an image, and you can feed it through a neural network. It will understand there's a dog there. So it can also place the dog, so the object location. It knows there's a bicycle there. But that's only in the image, and I try to move that to 3D. And the context of that was semantic exploration. So you try to have some meaningful exploration. So this example here is Venice. This summer I've been to Venice for the first time. It was very interesting. And whenever I go to a new city, I also try to explore it a little bit. And what you see here is very famous Piazza San Marco. And if you, or I don't know if you've been to Venice, but when you went there, you probably you don't just walk on Piazza San Marco and you're like, oh, okay, it's like 300 by 50 meters. And they're like, okay, that's the space. But you actually see, okay, there's the Basilica, there's the clock tower. And you realize, oh, I can maybe look around, look at the Basilica from different views. I can maybe go inside because it's a building, it's a church. So there's some meaning to that. And I try to replicate this exploring behavior on robots. So going back to this example with the object detection, we use 3D sensors and combine it with the camera to kind of move the 2D object detection, so the dog, which is just this frame, into 3D. So here's an example from my living room. And you see with the steps A, B, C, D, we can extract just the sofa in 3D. And this is the robot system we use. So you see on the left we have a Google Tango device. I think there's a demo for that here as well. So I can record not just images, but also some 3D data. And on the right you can see the little robot. So it drives around with the camera and the computation. And to run some experiments, I put it into a simulator. So on the left you can see the output of the system I described earlier, so you can actually map these persons in 3D. And I placed several persons in this simulator, so you have a top-down view of the environment that I built for the simulation. And you will notice that most of the objects are on the right-hand side of the map, and that's to test if the robot is really curious about these objects and if the algorithms that we built, if they have some effect on the behavior. So this is simulation video. You can see all the little blue dots moving. That's individual robots moving. So they're not moving at the same time, but they're just different simulation runs over several hours of simulations. And you can see they're gradually exploring the map, and we're also recording some statistics on the right side. It's not so important, but you will see that they basically just spread out. And after 5 minutes, you can stop the experiment and see, okay, what happened with the robots on average. And so the little blue dots are the individual simulator runs. and then there's a big pale blue dot, and that's the average of all the robots. And you can see if we're just naively exploring the space or just trying to go everywhere, you will see that the robots just spread out and that the average will stay in the center. However, with the semantic exploration, which will also care about looking at objects, you will see that the average moved or shifted towards the right, where all the persons are in the simulation. So we really get this nice high-level result that they will try to go where the interesting stuff is. Yeah, so that's nice, and these are all rolling robots, but now I'm going to hand it over to David, who will talk about these walking robots. David.
Thank you. So first, let me talk about the platform that I am working on a day-to-day basis with. So I am doing a PhD at the Robotic Systems Lab at ETH Zurich in conjunction with NVIDIA. We are working with this wonderful quadrupedal robot called Animal. It is equipped with a whole range of sensors that enable its autonomous operation. Legged robots have several advantages of a different kinds of robots that make them particularly suitable for search and rescue missions after natural disasters. They can carry more payload and have longer autonomy than flying robots, and they can overcome obstacles wheeled robots would get stuck on. In my research, I want to develop navigation and locomotion algorithms that enable these robots to successfully accomplish missions in such harsh environments. This is, of course, very challenging, and deep learning is a novel yet promising approach to overcome them. So imagine we have our robot Animal that is accomplishing a mission in the sewers, and it obtains the following image. What we try to achieve is to train a neural network that, given this stream of images, makes decisions and sends commands to the robots that ultimately lead to the success of the mission. At the core of this problem is a machine learning technique called reinforcement learning. You have probably heard of its most prominent applications with AlphaGo, Google DeepMind's artificial intelligence that was able to beat world-class players in the game of Go. What I particularly like with this technique is that it is very similar to how we humans pick up a new task. We make a decision, get feedback from the world, and learn from this experience. By repeating these steps for long enough, we get better and better at the task. As you can see on the left image, we have a bipedal robot that is learning to walk. It is clear that in early generations, it fails at the task. This is because it hasn't gathered enough experience yet. At some point, it is able to walk in a robust manner. Unfortunately, learning on the real system with such algorithms is very cumbersome because they require massive amounts of data. So imagine you want to train Animal on a locomotion task, so you would need at least 2 people that have to supervise the experiment. Then the Animal at the beginning would always fall down because it hasn't learned a lot. And of course, since you need millions of sample data points, this just takes too long. So the trick we apply here is to train the neural network in a simulation environment that can run much faster than real life, and then directly transfer the knowledge to the real robot. Coming back to our navigation examples, we also want to train such networks in a simulation environment. And thus, we need to find ways to generate such images in an artificial manner. And of course, since the network has to run on the real hardware, these images have to look as realistic as possible. This is very challenging because the image formation process is complicated, and there are many details that have to be taken into account. As we can see here on the image, we have reflections and shadows. NVIDIA is putting a lot of effort in the development of technology that enables the generation of very realistic-looking content. This is, of course, mainly driven by the film and gaming industry, but more and more we see that these technologies are integrated into robotic solutions such as the Isaac SDK you have heard of this morning. This is why we are very excited to work with NVIDIA and hope we are able to shape the future of robotics. Thank you very much.